rising tide, Grothendieck on simplicity and generality.
Yeah. This is Grothendieck and Serre, and actually I always have to check which is which. It's Grothendieck on the left. This is just about when they met each other. This is going to be very much a talk about the two of them. Around 1949, published in 1949, André Weil conjectured a deep connection between number theory and topology. Around 1953, Jean-Pierre Serre took it on as a project and began recruiting Alexander Grothendieck to work on it. Serre created a series of really concise, elegant tools, which Grothendieck and his co-workers then simplified into thousands of pages of category theory, making it, in Grothendieck's words, tout ce qu'il y a de bébête, infantile in its simplicity. There is a constant problem in translating Grothendieck because bébête can also be a boogeyman. Bébête can be various other things. In context, I think Grothendieck is not interested in playing on words. In the context, I think he sees this as simply meaning infantile, and yet that's not all the word means. It did work, and in fact, Miles Reed, among others, has said that Grothendieck himself can't necessarily be blamed for category theory, since his own use of categories was very successful in solving problems. Grothendieck, on the other hand, Grothendieck's memoir, Récolte Semaille, makes it plain that he thinks he has been blamed for category theory and for Grothendieckerie in general. Grothendieck describes two styles in mathematics. If you think of a theorem to be proved as a nut to be opened, so that you can reach what he calls the nourishing flesh within, the principle of the hammer and chisel is you put the cutting edge of the chisel against the nut, you strike hard, repeat at various places if necessary until the nut cracks open and you're satisfied. But Grothendieck says that he has a different strategy. He says, I can illustrate the second approach with the same image of a nut to be opened. The first analogy that came to my mind is of immersing the nut in some softening liquid, why not simply water. From time to time you rub so the liquid penetrates better, otherwise you let time pass. The shell becomes more flexible through weeks and months. When the time is ripe, hand pressure is enough, the shell opens like a perfectly ripened avocado. And then he says, another image came to me a few weeks ago. The unknown thing to be known appeared to me as some stretch of earth or hard marl, resisting penetration. The sea advances insensibly in silence. Nothing seems to happen, nothing moves. The water is so far off you hardly hear it, yet it finally surrounds the resistant substance. This is the strategy of the rising sea, the swelling sea. Well, this is another translation problem. The French is la mer qui monte. Again, any of Grothendieck's friends in post-68 psychoanalytic French circles would have seen this as a pun for le amer qui monte, the rising bitterness, and la mère qui monte, the lying mother. I believe Grothendieck is completely unaware of that. On the other hand, it's entirely impossible to translate into English. Are we to take mer here? If we say a rising sea in English, to me this suggests a storm. This image includes storms. If we say a rising tide, well, this image includes the rising tide in French. At any rate, it's this water surrounding the problem and finally solving the theorem, perhaps. Deligne supports Grothendieck's idea on this, describing one of his proofs as a long series of steps where nothing seems to happen, yet at the end a highly non-trivial theorem is there. I want to look at this style, at this style in several strands of Grothendieck's work. Grothendieck identifies this as his own approach and also as Bourbaki's. And this opens a very interesting theme in Grothendieck's comments on his own work. Grothendieck consistently not only advocates that research and teaching and exposition should all be done the same way, Grothendieck sometimes forgets that they aren't the same thing. So he'll compare his research techniques to Bourbaki's éléments as if they're all doing the same thing. I want to look at this and see a little bit about what it means philosophically for mathematics. I see this as a really extreme form. I see Grothendieck as having adopted the most extreme form of what Kant meant by the freedom of mathematics. For Grothendieck, mathematics works by creating new worlds. Now, Grothendieck uses this image of creating worlds himself, but in a little bit different sense than I mean, more epistemological and less mathematical. It's what he also calls building beautiful houses, framing theories and methods that become a heritage others can work in. He's certainly done that. So has Jean-Pierre Serre. I think of Serre's work on spectral sequences and, well, in so many fields. But I want to look at the difference between Serre's and Grothendieck's work. Grothendieck describes Serre as very yang against his own yin. He says Serre generally uses the hammer and chisel, not at all to say that Serre is heavy-handed. Grothendieck describes Serre as the incarnation of elegance. And that, I think, is the point. Serre creates these concise, elegant tools that cut to an answer. Grothendieck creates, on one hand, really massive books with numerous contributors, and also, technically, these set-theoretically huge, but logically very weak contexts. This is, well, it's something I try to bring up often with logicians. A Grothendieck topos is the size of the universe of sets, and yet what he wants of it is a very weak logic. The example of Serre and Grothendieck gets at another point, too. As Grothendieck says, from 1955 to 1970, Serre was at the origin of most of his ideas. He says he didn't realize that until he started reflecting on it for an autobiography, but every major step that Grothendieck took towards the Weil conjectures comes from Serre. This is a really deep collaboration. The only one I can compare it to is Dedekind and Netter, with, of course, the salient difference that Serre and Grothendieck spoke together. Another difference I would say is that Dedekind and Netter, I think, have very much the same style at base. I mean, that's arguable, but I see it that way, whereas Serre and Grothendieck really have quite opposite styles. This matter of really deep collaboration, I think this is an important historical issue that's especially typical of 20th century mathematics. I'd like to know a lot more about it. I will say, just in a nutshell on this, I think that the most important and challenging remark anybody's made about the nature of 20th century mathematics is Emmy Netter constantly saying it's all in Dedekind. I think in some very, very deep sense it is all in Dedekind, and yet it certainly took a genius of her order to have any chance at seeing that it was there. The story here actually starts with the Weil conjectures, and this gets to another issue we've talked about some here. Is André Weil a French mathematician? Now, culturally, you could not be more so. And if André Weil is not a French mathematician, then is Bourbaki a French group? Indeed, Weil wrote several times on French science, but he clearly depicts himself as a French mathematician in exile. He's actually rather bitter that he's not in France. In 1947, he was in Chicago feeling very much the exile. He describes himself as bored and depressed in a morn winter, in a depressing winter. He started thinking about finite fields, which, as we've heard, was a Chicago heritage, although he says he gets it from Gauss. And in 47-48, he proves some arithmetic theorems on curves over finite fields. On the one hand, as I say, the finite fields are in a way a Chicago heritage. On the other hand, his conjectures on these depend on a remark that someone pointed out to him about Poincaré's homology of algebraic varieties. I think we sometimes forget that Poincaré invented algebraic topology for algebraic varieties because it was never really able to apply specifically to algebraic varieties for decades. So these conjectures come to him even with a direct tie to Poincaré. The conjectures have to do with solving Diophantine equations, of course, and this can be very difficult. And Weil describes one strategy in a fascinating letter to his sister. His sister is on one short description, a Jewish born Catholic convert, socialist, pacifist philosopher. He writes to her that in solving these equations, which can be very hard, one strategy is to work over richer fields than the rational numbers. He mentions fields of rational functions over the complex numbers. These fields are quite different from the integers, and he says, we would be badly blocked if there were no bridge between the two, and voila, God carries the day against the devil. This bridge exists. It's the theory of algebraic function fields over a finite field of constants. Now, actually, there are people here who could probably give me some more advice on this. I do not see this as a bridge between Diophantine equations over the rationals and function fields over complex numbers. I see it as a third case that with analogies in both. I don't see it as intermediate, but perhaps other people can correct me on that or confirm it. The idea, of course, is that a polynomial might have no integer solutions. Just have a trivial example. This one has no integer solutions because x and y would have to be small. There's only a few things to check if they don't work. But it does have solutions modulo 5. Solutions modulo given prime are easier to find than integer solutions. This has actually been talked about in some other things here too, besides that it's in no way an obscure point. To see if a list of polynomial equations have a solution modulo p, you only have to check finitely many values, which might be a finite number. It's not really feasible to work with for a large prime, but it's still easier to work with than modulo a prime. What they considered, though, was how does the number of roots increase as we allow irrationals of higher and higher degrees? If we adjoin roots of cubic polynomials, roots of quartic polynomials. And of course, the thing is that over a finite field, all you need to know is what degree of root you've adjoined. And that determines the extension. So he's going to investigate how the number of roots increases as you admit higher and higher degree irrationals. An answer to this doesn't directly answer the question about integer or rational solutions, but it might help. It's interesting in itself. And it's turned out to have a lot of unforeseen applications. Apparently it has applications to planning optimally efficient networks. I don't know how. At any rate, building on earlier number theorists, they conjectured a penetrating form for the exact answer and some useful approximations. And more than that, he conjectures an amazingly simple link to topology. And so I want to look at the Weil conjectures just very briefly. For a smooth projective variety of dimension n, we're not concerned with details, we'll let ns just be the number of points defined on the degree s extension of a finite field Q. And then we define the zeta function, which is just summarizing the series ns in this form. This part of the reason that I want to get this up, this is, of course, a different kind of simplification. This is a classic, almost 19th century way of capturing a bunch of information in a simple form. Of course, it doesn't look simple at all at first. They make some conjectures about this, that zeta of t is a rational function, which, actually, no, I don't have slides of the explanation. To say that zeta t is a rational function puts very strong constraints on the numbers ns. It says that there's a finite list of complex numbers, a1 through ai and b1 through bj, say, so that ns is just the sum of s powers of them. This tells you a lot about those numbers. Conjectures a functional equation. On the one hand, these all are analogs to Riemann's zeta function, but they also have clear meaning in this context. The functional equation says that a certain simple algebraic operation permutes the a's and b's, the numbers whose s powers add up to ns. The Riemann hypothesis says what the absolute values of the a's and b's are. And over it all is this connection with topology. Take those same polynomials. Now, these could be polynomials over an algebraic number field, but those are all complex numbers, so you can look at them as just complex polynomials. And look at the Betti numbers of the complex manifold defined by the same polynomials. That is, just count the handles, the holes, on that manifold. Then each of the polynomials in that rational representation of the zeta function has degree equal to one of the Betti numbers. So the Betti numbers then control the absolute values of the roots of the polynomial, and E, which occurred in the functional equation, is the Euler number. It's the alternating sum. So the numbers of roots are very tightly tied to the topology of this manifold. It's really worth keeping in mind from a later point of view. This manifold has no interest in which numbers are rational, irrational. This is just a topological manifold, and yet its topology is controlling a great deal about the arithmetic. They proved several kinds of cases of this. These proofs make the focus of 5 chapters in what is a terrific book I'm about to complain about in a minute, but Ireland and Rosen, A Classical Introduction to Modern Number Theory. What I'm going to complain about is that book mentions none of the connections with topology and manages to describe the history of the Weil conjectures through Deligne's proof and mention Hartshorne's exposition of it without naming Grothendieck. The connection with topology is gone. The connection with Grothendieck is gone. It's simply a question of number theory, and it was solved by Pierre Deligne. Now, Weil, meanwhile, had pointed out already in 1948 that this whole series of conjectures would follow very quickly if we could treat the spaces of solutions over the finite fields, not the continuous complex space of solutions, but if we could treat the space of solutions over the finite fields as topological manifolds, the Lefschetz fixed point theorem would reduce the whole series of conjectures to a pair of graduate exercises in linear algebra, quite literally a pair of graduate exercises. They are exercises 24 and 25 of chapter 14 in Lang's algebra. Their trivial consequence is the existence of Jordan canonical forms of matrices. This conjecture needed someone of Weil's character, someone with really encyclopedic knowledge, someone completely unafraid to think about what looked like a remote connection and then believe something simple about it. The intuition was powerfully seductive. It drew a lot of attention right from the start, but it was seriously remote from existing tools. Weil's arithmetic spaces were not precisely defined at this point. To all appearances, they'd be finite or maybe countable, so they would be everywhere discontinuous. Topological manifold methods couldn't begin to apply to these things. And this actually raises another issue, about a historical issue about collaboration influence that I want to mention. I'm not going to go into it. This one's much harder to research. It seems that Weil himself rejected this strategy as he saw it carried out. He didn't like the way it was carried out. He didn't like the amount of apparatus it used. And besides that, there seemed to have been personal conflicts between Weil and Grothendieck that, well, I even say personality conflicts. It wasn't over issues, it was just personality. So that's complicating his contribution to it. At any rate, Serre liked this strategy. And Grothendieck says that the reason he was sold on it was that Serre showed him the importance of this way. We're going to prove these theorems by a cohomology theory for these arithmetic spaces. And Serre's approach was to use Sheaves. Oh. No, I'm missing a slide here that would have been helpful. Anyway, I just am missing it. I'm sorry. Sheaves were a new method at that time in topology that he and others were exploring. Grothendieck would later describe a sheaf on a space, and here's the missing slide, as a meter stick measuring t. If you could put these meter sticks on Weil's arithmetic spaces and you could prove standard topological theorems that way, well then you'd get the Weil conjectures. Now, by the nuts and bolts definition, a sheaf on a topological space is an assignment of abelian groups to the open subsets of T plus group homomorphisms from the group over any open subset to the group over any contained open subset, and these are subject to a covering condition. I do like to mention that in logicians' terms, these were Bethe models of the abelian group axioms. They're Kripke models with a covering condition. But, of course, precisely these nuts and bolts were unavailable for the Weil conjectures because you didn't have the kind of topology that had any promise at all. Now, at the École Normale Supérieure, Henri Cartan's seminar spent 1948 and 49, and then 1950 to 51, focusing on sheaf cohomology with Samuel Eilenberg often presenting sessions. Serre, then in his early 20s, ran sessions, and Grothendieck, 2 years younger, attended. I don't think there's any trace in the proceedings that he was there, but he was there. One motive for these seminars was that there were a lot of cohomology theories. Besides the purely topological ones, there was de Rham cohomology on differentiable manifolds, which not only described the topology of the manifolds, but also captured some differential analysis on them. And Cartan saw how to modify sheaf cohomology as a tool in complex analysis. For a complex analytic variety, Cartan could define sheaves, his coherent sheaves, that reflected not only the topology of V, but also complex analysis on V. He and Serre would develop this over coming years. These were promising for the Weil conjectures because clearly a Weil cohomology was going to have to reflect not just the point set topology of the spaces, if the spaces could ever be defined, because the point set topology just had no promise of being sufficient, but also algebra and arithmetic on those spaces. But understand, this differential analysis and complex analysis used sheaves and cohomology in the usual topological sense. What they did was they found particular new sheaves that captured analytic or algebraic information that was then revealed in their cohomology, things that a topologist might not have focused on. It was not a new definition of sheaf or of cohomology. You just found the cohomology of certain sheaves that would reveal this structure. The greater challenge to the seminar Cartan was that along with the cohomology of topological spaces, they looked at the cohomology of groups. I do like this story. I've told it to several people here, but I'll say it to the collection of you. Also, I was talking. No, maybe I won't. I'm sorry. I guess I won't because I'm still on videotape. It's not a humiliation to anyone, but it's something I wouldn't put on videotape at all. So they were doing group cohomology. Here the role of sheaves was played by G modules, which in logician's terms are permutation models of abelian groups. It's an abelian group with an action on it of another group, not necessarily abelian. These are formally quite different from topological sheaves, and this cohomology was formally quite different from topological, but it had grown out of topological cohomology. In fact, Eilenberg and MacLean had created category theory and their framework, along with Steenrod, for cohomology, largely to explain the link between what, by the time they were done, was topological cohomology on one side and group cohomology on the other. So they're tightly tied, but formally quite different from each other. So they were looking for links between these two. The seminar aimed to find what was common to the two kinds of cohomology, and they found it in a pattern of functors. For topological cohomology, we're going to look at the cohomology of a sheaf. If you're used to the ordinary Betti numbers on a space, you take the constant sheaf of the integers on it to get the ordinary Betti numbers. The cohomology of a sheaf on a topological space is a series of abelian groups, the cohomology in each dimension n, so that for each map F we have a series of homomorphisms, one in each degree. These homomorphisms form a functor. They have various properties that I'm not going to go into, but the decisive one is that the nth cohomology of any fine sheaf for n greater than 0 is 0. The cohomology of fine sheaves vanishes above degree 0. The cohomology of a G module over a group G is a series of abelian groups, again for each homomorphism, a series of homomorphisms, making a functor, satisfying the same formal requirements, with the difference that here what vanishes is the cohomology of injective modules. So where one uses fine sheaves, the other uses injective modules. A fine sheaf, this is a notion borrowed, well, finally from differential geometry by way of Cartan's complex analysis. A sheaf is fine if it admits partitions of unity. That is, for any locally finite cover of the space, you can break this sheaf up into parts, each of which is supported on one of those open sets. They add up to the whole, but each is confined to that part of the open set. A module is injective if, for every module inclusion and every homomorphism from the submodule into I, so I is injective if whenever you have a map to it from a submodule of M, there's at least one way to extend that to a homomorphism from M. On most of the details here don't matter. What I want you to see is these are completely different ideas. Suitable module categories gave group cohomology, profinite group cohomology, lots of different things. The seminar Cartan took the analogy no farther than this slide that I just had up. They present these two as analogous descriptions of cohomology, and that's as far as they go. And that caused real problems. The great outcome of the seminar was the book Cartan-Eilenberg with its declaration, which was, yes, we do have this. The book Cartan-Eilenberg begins with a declaration which was really a huge victory for Emmy Noether's methods. During the last decade, the methods of algebraic geometry, algebraic topology have invaded extensively the domain of pure algebra and initiated a number of internal revolutions. The purpose of this book is to present a unified account of these developments and to lay the foundations for a full-fledged theory. But this unified account was cut off from its own roots. It had to exclude its own beginnings. They could treat the cohomology of many different algebraic structures. They focus on groups, Lie groups, and associative algebras because these all used injective resolutions. These all killed the injective modules. They could not include topological spaces, which were historically the source of the whole idea, but also keep in mind they remain technically one of the main motives for all of it, because all of this was being developed in interaction with topology. They couldn't do that because it didn't use injective resolutions. It used fine resolutions, or Godemont then produced other variants, flabby and soft resolutions. In terms of searching for a Weil cohomology, a cohomology to prove the Weil conjectures, this approach left two questions. What would Weil cohomology use for Sheaves, and what kind of resolutions would it use? How would it resolve them to get a cohomology? Grothendieck unified all these cohomologies by rewriting Cartan-Eilenberg, and he makes it clear that his Tohoku paper he sees this as the way Cartan-Eilenberg should have been done. He repeatedly describes them as two forms of doing the same thing, and clearly he likes his. Among other things, he preempted the question of resolutions for Weil cohomology before anybody knew what kind of sheaves a Weil cohomology would use. They knew it was going to use injective resolutions. And he did this by asking not what sheaves are, but how they relate to each other. In his words, much later, in 1985, he says, what he set out to do was consider the set of all sheaves on a given topological space, or if you like, the prodigious arsenal of all the meter sticks that measure that space. And we're going to consider this set or arsenal as equipped with its most evident structure, the way it appears, so to speak, right in front of your nose. That is what we call the structure of a category. From here on, this kind of measuring superstructure called the category of sheaves will be taken as incarnating what is most essential to that space. As André Joyal once put it to me, there is no ontology here. That's the whole point. We're not saying that a topological space is a category of sheaves on it. We're not saying what it is at all. We are saying that what's essential to that space is captured by the category of sheaves on it. Also not what the categories are, but just what the sheaves are, rather, but just what category they form. The main point of the seminar Cartan on cohomology was that this structure right in front of your nose sufficed to organize much of cohomology. Definitions and proofs can be given in terms of commutative diagrams and exact sequences without asking most of the time what these are diagrams of, and that's what the seminar had done already. Grothendieck and Buxbaum, both independently, had pursued this idea, extending work that MacLean had done, I will say that Grothendieck said several times that when he created abelian categories, he was not aware of MacLean's work on it. And I'm sure that's entirely true. He was not thinking, he had not read any article by MacLean on it because he didn't read articles. He heard about things from Serre. He did not know of such an article. He does have to say a few times in Occulte Semi, when he's complaining very bitterly about people not giving the correct credit for work, every once in a while it comes to his mind that he never gave anybody credit for any work. So, because he wasn't in the business of giving credit, he was in the business of doing the work. But on the other hand, he was traveling, he was very much involved in MacLean circles, and in fact, he was working in Kansas in the Midwestern United States when he did the work on that became the Tohoku paper. So, and also what I think people haven't always noticed is that MacLean did use the term abelian category in his work in 1950. So I think there's just really no chance that MacLean's 1950 work didn't influence Grothendieck's later on. But Grothendieck went farther than anybody else before had done, insisting that this formal analogy between sheaf cohomology and group cohomology should become, quote, a common framework including these theories and others. It's not to be an analogy, it's to be an actual tool that works in all these cases. He gave diagrammatic axioms for the basic properties used in cohomology and called any category that satisfies them an abelian category. He gave further diagrammatic axioms called AB3 through 5 and existence of a generator, tailored to support Baer's original proof that in module categories there are enough injectives, that every module embeds into an injective. These and what he did, he looks at the original proof and he sees that it's very diagrammatic. Baer's reasoning already in 1940, although it's specifically about abelian groups, and he's very interested in their nuts and bolts, still his reasoning doesn't refer to the nuts and bolts much. It refers to patterns of maps between them. And Grothendieck then just says, so we'll take a category in which those patterns can always be depended on to exist. And then we'll get cohomology over such categories. So he finds these properties, these axioms on a category, and it's very easy to see that the category of sheaves over a topological space satisfies these axioms. So the injective resolutions are possible for sheaves over any topological space. In a category, we say an object is injective if for every monic from n to m and an arrow to I from n, there's at least one. All we've done is instead of say group and homomorphism, we said object and arrow. It's the same definition. Now, this proof that topological spaces have enough injectives is not the easiest proof of that theorem. There's a quick, direct proof of that's known, and Weil has shown in his history of homology that the direct proof it's almost given in the Séminaire Cartan. All the steps of it are there, and yet the issue just doesn't seem to have been raised. This final unification where all the cohomology theories really are following exactly the same pattern, they didn't seek it, they didn't find it, but Grothendieck delivers it here. So Grothendieck's theorem shows that sheaves on, but also it's not just that he unifies this with the fine resolutions didn't work on all topological spaces. Fine resolutions only gave a nice theory over paracompact spaces. A paracompact space is it's a Hausdorff space where every open cover has a locally finite refinement. From the point of view of differential geometry, not a problem. Differential manifolds are all paracompact. From the point of view of analysis, not a severe problem. It was a problem for the Weil conjectures because the kinds of topologies that you get in algebraic geometry are basically never Hausdorff, except in trivial cases. This in fact, I would like to be reminded who told us this story. Someone was saying the other day that Zariski was very concerned that his name should not be associated with the Zariski topology because it's a triviality. Peter Fried once told me that if you ever really want to do in a mathematician, what you do is you find some trivial remark they made somewhere, and call it their theorem. Name it for them. And the Zariski topology in one way is trivial, but precisely this kind of thing shows you what the experience of any number of graduate students also shows. The Zariski topology was not easy to think of. The Zariski topology doesn't act like a real topology. Points don't have disjoint neighborhoods in it. Well, we all know a topological space doesn't need to be Hausdorff, but would you want to use one that wasn't? Well, yes, you would. But the seminar Cartan theory of topological spaces, topological cohomology, couldn't use it because it's not Hausdorff, it's not paracompact. Grothendieck's method doesn't care whether the thing is Hausdorff or paracompact. Now, in the case that it is, it agrees with the seminar Cartan approach. So you can still use flabby resolutions if you want, you can still use fine resolutions if you want, and you will want to at times. But you now have a theory that works for all topological spaces and works for them all the exact same way that it works for modules over a group or continuous modules over a profinite group over and over again. It's the exact same. This generality had another advantage in that it simplified homological algebra. I'll just put Grothendieck up here because he's more interesting to look at than an injective module. It simplified homological algebra just by focusing on the relevant features. Textbooks today rarely use the generality in principle, textbooks on homological algebra even. They rarely even discuss sheaves on topological spaces, but they are organized in abelian category terms. And I just mentioned three influential examples. Eisenbud's commutative algebra takes a common strategy where abelian categories are not actually defined, but they're referred to. And the fact is that the definitions and proofs he gives are essentially in abelian category terms so that you can carry them over into that anytime you want to. If you want to learn that generality, you've already seen the proof in that generality. Hartshorne's algebraic geometry does give the abelian category axioms and very explicitly uses theorems from them as a basis of cohomology, but he doesn't give proofs of them in that book. He refers to several strategies for proving those theorems, one of which is to deduce them from the axioms. He gives others as well. And most extremely, Lang's algebra in the first and second edition, which had that famous exercise, he gives the abelian category axioms, and then as an exercise says, take any book on homological algebra and prove all the theorems without looking at the proofs given in that book. That's not in the third edition. Eisenbud speculates that maybe because he has moderated his view, but another possibility is because the axiomatic viewpoint is so much more widespread now. Probably the book you'd pick up uses it so that the exercise won't work. In particular, Serre's key contribution to the Seminar Cartan and in his dissertation, which was published in the Annals of Mathematics, was to clarify spectral sequences and extend their range and power. A spectral sequence was and is a tremendously powerful device for computing abelian groups or modules or things like that. They remain the standard technique for any kind of non-trivial calculations in cohomology. A spectral sequence is an infinite series of infinite two-dimensional arrays of abelian groups and group homomorphisms, with each successive array gotten from the homology of the one before. So we start with an infinite array here going off in at least two directions, and then we take homology, and that gives us arrows this way on this infinite array and that way on this infinite array, and it goes on like this. And the point of all of this, typically, is to calculate a few groups that live just in this little corner of it. It's typically not feasible to go much farther than that. You invoke this huge amount of apparatus to get a few conclusions. There is no difficult step with spectral sequences. No particular thing about spectral sequences is difficult, but they're intimidating just from their bulk. It's hard to get a grip on them just because they're so big. And it was only in 1955 that Grothendieck wrote to Serre, "I have lost my horror of spectral sequences," and the way he did it was by showing that you can prove everything about them from the axioms in the Tohoku paper. in this 1957 paper on homological algebra. The whole point of spectral sequences, of course, is to let you calculate in an orderly way without worrying very much about what's going on in each of those vertices. And the abelian category axioms formalize that simplification. You can prove these theorems without having posited that anything is going on in the vertices. Although, of course, in applications it will be, and your conclusions will follow. In effect, a few pages of definitions of Sheaves, resolutions, and derived functors from the seminar Cartan or from Serre's dissertation were simplified into 102 pages of category theory. You can imagine that many people found the work completely disproportionate to the problem. There's a legend that it took 2 years for him to find a publisher for what has become just a standard reference in homology. That may be a bit overstated. We learned from the Serre-Grothendieck correspondence that Eilenberg was ready to put it in the transactions of the AMS in 1956. With some editing, Grothendieck said he would do the editing only if someone else would retype the manuscript. We don't know what kind of editing it was. One possibility, Eilenberg wanted a few things clarified, and Grothendieck said, I won't retype it. Another possibility, Eilenberg said, I want it 2/3 this length. And Grothendieck just saw red and wouldn't think of it, which is probably very hard to tell at this point what happened. At any rate, abelian categories became and remain the standard setting for cohomology theories. This was a major step in understanding cohomology, and I'm sorry I haven't got a slide on this either. How can I not have a slide? Anyway, I don't. As Deligny put it, Grothendieck had shown that given a category of Sheaves, a notion of cohomology groups results. But he'd actually shown more than that. He'd shown what a category of Sheaves was. It's an abelian category. It's an AB5 category with a generator. Once you have any abelian category with these a few other properties, that gives you a canonical cohomology theory. So now our problem in proving the Weil conjectures is simply to find which abelian category suits each of these arithmetic spaces. We know what injectives it'll use. We know what definition of cohomology it'll use. We just have to know which abelian category. Grothendieck never mentions abelian categories by name in his autobiographical memoir, Récolte Semaille. That memoir focuses on more controversial ideas. Abelian categories were never a particularly controversial idea. He does cite the paper, the Tohoku paper, in an enlightening way. He cites it as an explanation of toposes, which he had not defined at the time he wrote the paper. He tells us a space in the nouveau style, or topos, generalizing traditional topological spaces, is given by a category which, without necessarily coming from an ordinary space, nonetheless has all the good properties, which have been explicitly designated once and for all, of course, of such a category of Sheaves. And he explains that by the good properties, he means exactness properties as he had explored in the Tohoku paper. Now, be clear, they are quite different exactness properties. A topos has quite different properties from an abelian category. What they have in common is that these properties are specified categorically. And so this is typically how he cites a Tohoku paper. It explains what a topos is. I will mention also, a topos is a category of sheaves of sets. An abelian category is a category of sheaves of groups. But, well, that's detail. In fact, the variant ways that Hartshorne mentions for proving theorems on abelian categories are all different ways to understand how abelian categories lift properties from the category of groups. And Grothendieck uses this way of thinking. As abelian categories lift properties from abelian groups, so each topos lifts properties from the category of sets. And Hartshorne, his different strategies for proving things in abelian categories are different ways to understand that lifting. One of the strategies he gives is that every abelian category with a generator embeds into the category of abelian groups. So you want to study this abelian category, embed it into groups. You study what happens in groups, and that comes back across the embedding. In this sense, you've lifted properties from groups into abelian categories. Another, of course, is to just give proofs directly from the abelian category axioms, which, after all, also characterize the category of abelian groups. And as MacLean had already mentioned in 1950, often those are the properties you use in a proof. So you lift the properties axiomatically. And another strategy is diagram chasing, where instead of looking at elements of abelian groups, you look at generalized elements of objects in any abelian category. They act rather like elements of an abelian group. Hartshorne doesn't include that strategy, but MacLean, for example, has often stressed it. And this is the really deep simplification that Grothendieck proposed. The way to understand a mathematical problem is to express it in the mathematical world most natural to it. And that's what a cohomology theory does for him as he's understood it. In particular, you express it in the topos natural to it. And with luck, the cohomology may solve your problem. Let me give you my outline of that first, and then a quote from Grothendieck to support my interpretation. The right way to approach a problem, Grothendieck is beginning to feel by 1958, is find the natural world where it lives. And this is going to be a big world. This is going to be a topos. In the case of the Weil conjectures, you find the étal topos of an arithmetic scheme. He doesn't really have that idea very clear in 58 yet, but you express your problem cohomologically. And, for example, state the Weil conjectures as a Lefschetz fixed point theorem. And the cohomology of that world, well, when I say solves, may solve your problem, like the bursting of a ripe avocado. Here, let's see it in Grothendieck's own words. The crucial thing here, from the viewpoint of the Weil conjectures, is that the new notion of space is vast enough that we can associate to each scheme, well, I'm just about to get to what schemes are, but these are what represent those arithmetic spaces, a generalized space, or topos, called the étal topos of the scheme in question, certain cohomology invariants of this topos, tout ce qu'il y a de bébête, as infantile as they could be, seem to have a good chance of offering what it takes to give the conjectures their full meaning, and who knows, perhaps to give the means of proving them. So he's being very clear here that the topos embedding is the way to understand the problem. It may also be the way to prove the theorems. The unity that was being sought in the seminar Cartan is now absolutely complete. Cohomology is a theory of the algebraic invariance of a topos, the way people used to think it was the algebraic invariance of a topological space. Every cohomology theory for Grothendieck, of course there are extraordinary cohomologies, lots of things called cohomology theories, but in Grothendieck's mind, every cohomology theory is simply the invariance of a topos, the way it used to be of a topological space. Grothendieck notes that his Tohoku paper gives foundations for the cohomology of any topos. Toposes were hardly foreseen when he wrote that paper. This is one more proof that it's the right cohomology theory, because it works in unforeseen generality. For the Weil conjectures now, it only remains to tell what topos each arithmetic space naturally determines, recalling that in 1955 the arithmetic spaces themselves had not been precisely defined. In fact, this phrasing of the problem in terms of toposes came to Grothendieck at the same time as the solution in his theory of schemes, plus Serre's idea of isotrivial covers. I'm not really going to get to isotrivial covers. As to schemes, well, here I'll put Serre up. There's a story, I don't know how well it can be documented, of John von Neumann speaking about Hilbert spaces at Göttingen, and afterwards Hilbert takes him aside and says, Johnny, tell me, what is a Hilbert space really? My German isn't very good, but I think the German is better. Was ist aber eigentlich ein Hilbertscher Raum? What is the proper of a Hilbert space? Well, apparently, von Neumann had given the axiomatic definition, some examples, some theorems, and Hilbert wanted to know better what was the key idea here, what's really behind it all. There is also a story, and the person I got it from told me I cannot attribute it to him, that at a Parisian cafe in the mid-1950s, Grothendieck asked his friends, what is a scheme? But this time the point is very different, because the definition didn't exist yet, only the key idea did. It's a perfectly natural question for him to have asked. He's visiting from Kansas. He hears all this talk. He says, well, what are these things? And with all the more right, because nobody has defined them for him, because they don't have a definition yet. Here were some definitions of scheme using the word The words, well, actually, Serre didn't, but Chevalier did, and other people did. Really, the history here is to see how Grothendieck is going to simplify an 80-page paper by Serre into 1,000 pages of the Éléments de géométrie algébrique. And he's going to do this essentially by achieving Kroneker's vision of an algebraic geometry over the integers. Not at all, of course, in Kroneker's way. Not to say that Kroneker would have said just what I had in mind. And the first step here is to understand why Serre has very well said that no one invented schemes. One often says that algebraic geometry deals with spaces defined by polynomial equations and deals with them in terms of the algebra of those polynomials, but of course that's a pedagogical abstraction from a body of work that uses a whole lot more than rings of polynomials. Dieudonné and Grothendieck by 1971, well, there's an interesting evolution here. When the first edition of Chapter 1 of Elements of Algebraic Geometry comes out, Grothendieck and Dieudonné say, we're not going to give a historical background here because it's beyond our competence. We can't do it. But when the Springer-Verlag edition comes out some 10 years later, they do give one. Well, Dieudonné is, sometimes you can really think you can see which is Dieudonné and which is Grothendieck in there. Dieudonné has been working on history of mathematics. They trace the basic idea behind schemes then back 100 years to Dedekind and Weber, apparently meaning their work extending a line of thought in Riemann where a curve over the complex numbers is studied by the algebra of meromorphic functions on that curve. On this approach, the ring of meromorphic functions is the basic object. In fact, it's a field of meromorphic functions, and the points of the curve are defined algebraically from it. Of course, this is not a polynomial ring. There were a lot of formal conceptions of algebraic spaces around by the mid-1950s in Paris, dominated there by Weil foundations using Weil's theory of abstract algebraic varieties. I was just looking at O.F.G. Schilling's enthusiastic but awestruck review of Weil's Foundations of Algebraic Geometry in the Math Reviews. This will dispel any thought one might have had that the ideas were more naturally geometric before scheme theory. Weil Foundations, people liked them, but it's not because you look at them and the geometry leaps out at you. And I just added in a footnote too, if you feel that maybe geometry is more intuitive with the Italians, intuitive in some sense, yes, but not in the sense that all you have to do is look at it and you'll see what they were talking about. It's not accessible at first to an outsider. But at the same time, especially responding to Weil's challenges, an undefined idea of schema was current in Paris. It more or less meant whatever generalization or reformulation of Weil's abstract algebraic varieties would turn out to be best. And it should work well for the Weil conjectures, but Weil himself had said, following Kroneker, we want an algebraic geometry over the integers. And this should somehow be included. Algebraic geometry up to then, including Weil foundations, worked over fields and really worked best for algebraically closed fields. So what you would do, you could work with a space over the rationals in Weil's foundations, but you probably wouldn't. You'd do it over the complex numbers. And then you could ask for the points with integer coefficients if you're studying Diophantine equations, but this is an extra bit of structure on your space. It's not intrinsic to the space which points have integer coefficients. It's not preserved by geometric isomorphism. And from Kroneker's point of view, this is, of course, quite backwards to start with the complex numbers and then pick out some of them as rational and some of those as integers as extra structure. Grothendieck, well, so here are some things that were current at the time. Chevalier's was typical of new ideas of scheme. We'll take a field and a finite type algebra L over K. So we're not saying polynomial here. We're making it more invariant than that, which is itself contained in a field extension of K. This gives a scheme whose points correspond to the local rings contained in L. The idea is that our spaces should be somehow more general than quotients of polynomial rings, but this is a lot of extra structure. Serre had said, well, what we'll do is we'll take an algebraically closed field. A variety over that field is going to be a topological space with a sheaf of germs of k-valued functions on it. So these are actual functions. So we have this structure sheaf. And what Grothendieck said in 1956 is, no, every commutative ring is going to define a space. How do we know we've got the right foundation for algebraic geometry? It will apply to every commutative ring. This is all needless complication. Now understand, everybody in these circles in Paris knew how you would do that if you were going to do that. At least once you told them, we'll use Sheaves. They knew what the points of the space would be. They'll be the prime ideals. They knew what the topology on it would be. It'll be the Zariski topology. If you told them we're going to have a sheaf of functions on it, say, okay, I know what the functions are in a closed subset. And that's classical, and it's not hard to guess what the functions are in at least some of the open subsets. There'll be localizations. So everyone, it's not that Grothendieck came up with a new idea of how to do this. What Grothendieck came up with was the idea that you should do it. And as Serre has told me in conversation, and I'm sure he said this in print, I just haven't found it, no one except Grothendieck thought that could work. Now there is Pierre Cartier who has said what Grothendieck also says of him in 1957, that he had a related theory. I have just not been able to find that. I just need to get in touch with Cartier and find it out. But apart from Cartier, nobody thought rings are too general. They're too weird. They won't have a nice geometry. But what you see in Hartshorne's algebraic geometry is the right answer, the answer that Grothendieck was pointing to, that of course you don't have a good geometric theory for arbitrary schemes. But the right definition is a definition of an arbitrary scheme. And then you add structure assumptions as you need them to support your theorems. And I can close with Deligne's comment on this. The audacity of Grothendieck's definition is to accept that every commutative ring A with unit. I kind of like that because when I grew up, I didn't know there were rings without unit. It was only when I started doing history of math that I learned they didn't have. So I like Deligne saying with unit. Has a scheme, spec A. This has a price. The points of the scheme, the prime ideals, have no geometric sense ready to hand, a nicely turned phrase, because of course they have a geometric content, but when one needs to construct a scheme, one generally does not begin by constructing the set of points. And he has said that if giving place to a space for every ring produces odd schemes, what it also produces is a category of schemes with very nice properties. These are the properties that Grothendieck and Dieudonné had already said. The whole point of these is that into these categories we can lift constructions familiar from sets. They say the readers will no doubt need an effort of thought, as the authors also did, to learn to lift those properties. But this is what makes it of infantile simplicity in the end. Thank you.